light and all of the different light equations and kind of an introduction to, why we do electron configuration. And I will start this video with a disclaimer. I'm not an expert on quantum physics or on modern physics or any of it. So my knowledge is admittedly, kind of limited when it comes to the quantum physicists of the 1940s and 50s. So I'll just tell you what you need to know for my class, and if you want to know more than that, well, happy hunting. Okay, so we're going to start with the wave description of light. There are two theories at work on light. One is that light is a particle, and one is that light is a wave. And the debate still kind of goes on today. It's kind of thought that, well, light's kind of both, but we're going to start with the wave and then go on into the particle. So electromagnetic radiation is the big technical fancy term for light, and it's a form of energy that kind of acts like a wave, but it can travel through space. And the way that light acts like a wave is that it has wave interactions. Like, it can be reflected, it can be diffracted, it can be refracted, it can be have positive and negative interference. And so that's how it behaves like a wave, but the fact that it can travel through space makes it kind of not like a wave, because the majority of waves are mechanical waves, meaning that they need to travel through some kind of medium. Like, the sound that is coming out of your computer right now is traveling into your eardrums by way of a sound wave, where the sound actually causes the air particles to vibrate in such a way that the sound can transfer energy from one particle to the next. Light doesn't do that. Light doesn't need to have, a medium to move, to transfer the energy through. It can just do it on its own. But the big thing is that light travels at a constant speed. Electromagnetic radiation travels at a constant speed of 3 times 10 to the 8 meters per second. This is the speed of light constant. It's a lot of times abbreviated with a C. And this has been a very much agreed upon constant for a very long time. There are a couple of not well-respected physicists that say the speed of light is slowing down, and has been ever since, the dawn of time. And you kind of laugh at it and take it with a grain of salt and say, well, when we first started measuring the speed of light, our technology wasn't that good, and so our measurements weren't that accurate, and as time has gone on, it's got more accurate, and we realized it's actually slower than we thought, yada yada. But at the same time, it was a not very well-respected scientist that said that the Earth orbited the sun. So you never know, and maybe one day we'll have proof that the speed of light is, for some strange reason, slowing down. I don't know. I hope not. That would kind of seriously jack everything up. So the electromagnetic spectrum is like a visual representation of all of the electromagnetic radiation. And if you're using the Holt chemistry book, then you can find it on page 92 of your book. So this is what the electromagnetic spectrum looks like. And they list the electromagnetic spectrum in order of increasing energy. So as you go this way across the electromagnetic spectrum, the energy increases. And so on this end, you have the radio waves, which are the lowest energy, and they're also the biggest waves. You can see here, radio waves range from 10 to the 3rd meters. Think about that for a second. What is 10 to the 3rd? That's right, it's 1,000. So 1,000 meters. So radio waves are huge. They're the sizes of buildings, which is why radio waves are so easily interfered with when it comes to buildings, or how you could stand in front of an old antenna radio and actually disrupt the signal because you are big enough to block a radio wave. They do have a very low frequency as far as waves are concerned, and they have the lowest energy. And then as you move up, you get shorter wavelengths, higher frequency, higher energy. And so you have microwaves here, and these are the kind of microwaves you're thinking of that, help us cook our food real fast. And then you keep going, increasing in energy, and you get to infrared light. And then you finally get to visible light, which is this tiny little sliver of the electromagnetic spectrum that we are actually capable of seeing. So if you look at this whole thing, we are capable of seeing this one little fraction of it right here. So, look at all these different forms of electromagnetic radiation that we can't see. And, you have animals that can see, more in this range, like bees can see more in the ultraviolet range. You have some animals that can see more in the infrared range. But us humans, we are right here. And if you've never met Roy G. Biv, allow me to introduce you. Roy G. Biv are the colors of the rainbow. Red, orange, yellow, green, blue, indigo, violet. And if you come down here, you can see that. Red, orange, yellow, green, blue, indigo, violet. And that's the colors of the visible spectrum listed in order of increasing energy. So as you go across like this, the energy goes up. So that means red has the lowest energy, whereas violet has the highest energy. And this is just within the visible spectrum. We're not talking about the whole spectrum, just within the visible spectrum. And so G is going to be right here in the middle with the medium energy. And because of the relationship between wavelength, frequency, and energy, the lowest energy corresponds to the highest wavelength and the lowest frequency, whereas the highest energy corresponds to the shortest wavelength and the highest frequency. And then you keep going up and you get into ultraviolet, and this is the electromagnetic radiation that gives us our lovely, wonderful, fantastic little sunburns. And then you continue going up, and now they're called rays instead of waves. And the reasoning behind this is because now the wavelengths are so small that at first glance it doesn't look like a wave at all. It just looks like a beam, a ray. And so they started calling them X-rays and gamma rays. These are the X-rays that enable you to be able to see your bones if you got, you busted a bone or something. And then the gamma rays that are given off in nuclear reactions. These pictures down here are just to give you size comparisons of how the different forms of electromagnetic radiation compare to things that you know about or have learned about in past classes. What do I expect you to know from this? Well, I don't expect you to memorize the wavelengths or the frequencies of any of these types of radiation. I do expect you to know the order, and so that you can answer questions about how they relate to each other. Which one has a higher wavelength, radio or visible? Which one has a lower frequency, infrared or X-ray? Know how they compare to each other. And for sure, you need to know Roy G. Biv. Okay, so wave calculations. We have a couple of formulas that I'm going to show you guys. And I'm just going to identify some of your variables now. A wavelength is the distance between two peaks if you're talking about a transverse wave. And it is in this particular section, it's measured in meters. And so if you had a wave, a wave would look like this. And, keep going. Well, the wavelength would be the distance between one point and the next point just like it. So it's always nice to, measure it between two peaks, or measure it between two troughs, or you could even measure it from one halfway between a peak and a trough and then the next halfway between a peak and a trough. But you'll notice all of these lengths are the same. And it's symbolized with the Greek lambda, which you just kind of write like that. And then you have frequency, and that's actually not a V. This is the Greek letter nu, which kind of looks like that. And that's the number of peaks that pass a point every second, some given point. So like if you were trying to find the frequency of ocean waves, easiest point to pick out in the ocean would of course be a buoy. So you would just count the number of waves that pass a buoy every second. And the units on that for frequency are waves per second. And since waves is just, it could be anything, you would just say 1 over a second or hertz. And this is your formula, C equals lambda nu, where C is the speed of light. And this is the physics formula of speed equals distance times time. The speed is the speed of light, the distance is the wavelength, and the frequency, the number of peaks that pass each second, is your time. So this is just your basic speed formula from physics, or from IPC if you took that, or from 8th grade science. This is a basic speed formula here. So is light really a wave? I kind of mentioned earlier that some scientists thought of light as a particle, and some scientists think of it as like halfway between the two. This guy, Max Planck, great little physicist, he did experiments where he saw how light and matter would interact and showed that light in these cases did not act like a wave. Now, I don't know a lot about his experiments, but I'll give you the best of what I know. He studied the photoelectric effect, which is where he shined different wavelengths of light on different metals. And what he found, do I talk about it yet? Yeah. Was that certain metals only got really good and shiny at certain energies of light. Now, if you have wave theory working, then that means the light is hitting the metal at a constant rate, and so it shouldn't matter what energy of light you shine on a particular metal, they should all make them shiny. Well, Max Planck proved that that wasn't the case. He said that, only specific energies would cause the photoelectric effect. And because of that, light can't be a wave. Light has to be individual quantized particles. So that led to the particle theory of light. And he said that the energy that the objects emitted were called quanta. And so a quantum is the minimum quantity of energy that can be lost or gained by a particular atom. And of course, he did his work with metal, so his original definition included the word metal in there somewhere. And so what he did was he was able to relate the energy of an electron contained in a particular atom with the frequency of EMR is electromagnetic radiation. So he related the energy of an electron with the frequency using that lovely little formula right here, where E is the energy, H is the constant that he figured out whenever he determined the relationship between energy and frequency, and this V is the same. It's not actually a V, it's a nu. And that's the frequency of radiation emitted, and of course frequency is measured in hertz. And energy in this case is measured in joules. So the two formulas that you guys need to know are this one and C equals lambda nu, the speed of light equation. So let's do some practice, shall we? What is the wavelength of yellow light? What is the frequency of yellow light with a wavelength of 548 nanometers? Now I told you back here that, let me get to that slide. Let's see. I told you right here that wavelength is measured in meters. And so we need to make sure to first convert our wave measurement of 548 nanometers to 548, or to however many, meters it is. So that's what I'm actually going to do first, is get this in the right form. So 548, left off my 8, nanometers. Now, how many nanometers are there in a meter? Well, nano helps you remember. It's 10 to the 9 nanometers per every 1 meter. So my nanometers cancel. If you have no idea what I'm doing with these boxes here, go back and watch my introductory stoichiometry video. It's a mole practice one, and you'll see, I'll explain what these are. And so basically the function that you have to do is 548 divided by 10 to the 9, and that works out to be 5.48 times 10 to the negative 7 meters. And you'll see that most visible light, so if it's any kind of colored light, that's Roy G. Biv, that's visible light, is going to be something times 10 to the negative 7, because the wavelength window, I guess, for frequency of visible light is in the 10 to the negative 7 range. Whoopsie daisy, sorry. Oh, I didn't mean to delete that. So let me fix that. 5.48 times 10 to the negative 7 meters. So the question wants to know, what is the frequency of yellow light with a wavelength? So we know wavelength. We're trying to calculate frequency. What's the formula that relates wavelength and frequency? Well, it's C equals lambda, wavelength, nu, frequency. So I'm going to rearrange this to solve for frequency. Actually, you know what? I'm going to go full out guess method. So my given, C, I always know, is 3.0 times 10 to the 8 meters per second. Lambda was given to me in the question, 5.48 times 10 to the negative 7 meters. So you see my meters match up so that they're going to cancel each other out later. And my nu is my question mark. So rearrange, this is my given, rearrange my equation to solve for my unknown, and so I know that frequency is equal to speed of light divided by wavelength. So that's my equation, and now I'm going to, this is my unknown right here, sorry I forgot the u part of that. So my substitution, wavelength equals 3.0 times 10 to the 8 meters per second divided by 5.48 times 10 to the negative 7. And look at that for a second and see if you can't estimate what it is that you're supposed to get. I'm actually using this as an excuse because I forgot my calculator. But the estimation on this, you take 3 divided by 5.48, let's about 1/2, a little more than 1/2. And then we know that whenever you're dividing exponents, you actually subtract them. So 8 minus -7 gives you -14. So we should expect something like 0.5-ish times 10 to the -14, which when we put into the correct sig figs, should give us something times 10 to the -13. Wait, I can't. 8 minus -7 is 15, not 14. I'm thinking ahead of myself, sorry. So 3 divided by 5.48. And you end up with our solution, solve, 5 incorrect sig figs, 5.47 times 10 to the -14, and that is going to be hertz. And so the other thing that you'll notice with visible light is the hertz, the frequency measurements, are always something times 10 to the -14. So if you remember that, then you can always know that you're on the right track there. What is the wavelength of blue light with a frequency of 4.6 times 10 to the 23rd hertz? This actually wouldn't be blue light. This would be somewhere in the ultraviolet range. So I really should change this to ultraviolet. Might even be more than that. I kind of just pulled this number from nowhere. So what is the wavelength? So wavelength is our question mark. Frequency is 4.6 times 10 to the 23rd hertz. And so the equation that relates frequency and wavelength is C equals lambda nu. So that means I'm going to need C as well, 3.0 times 10 to the 8 meters per second. And you might be wondering, on the last question I said 3 sig figs, even though this particular number has 2 sig figs. Really, you could have 3 or 4 or 5. It's like 2.9998989, something like that. I mean, it's so much 3. And really, you can carry this number out to about 4 or 5 sig figs and say 3.0000, and it's still fine. So I really don't consider sig figs whenever I'm doing calculations like this. So this is my given and my unknown. My equation, C equals lambda nu. And I'm going to rearrange it for my wavelength. So my wavelength is equal to C over nu. Whoa, I kind of wrote that wrong. Sorry. And C, of course, is 3.0 times 10 to the 8 meters per second. And then my frequency, 4.60 times 10 to the 23rd hertz. And the hertz and the seconds actually cancel each other out. And you plug this into the calculator, and you get, oh, that's not what I wanted to do, 4.60, 23. You get 6.52 times 10 to the -16 meters, because that's the only unit that is left, and we just did wavelength. So yeah, significantly shorter than your typical visible light wavelength. One more energy practice. What is the energy of magenta light with a wavelength of 691 nanometers? Again, just like on the first one, can't use nanometers. You got to convert this into meters. Well, from the first one, hopefully you remember that nanometers, 691 nanometers would be 6.91 times 10 to the -7 meters. If you don't know how I got that, just go back to the question 2 before this one. So now they want to know what's the energy. So energy is going to be my x. Well, I only have one formula that uses energy, and that's energy equals Planck's constant times frequency. Well, I have frequency. I have wavelength. So I know that H is Planck's constant, 6.626 times 10 to the -34 joules seconds. Frequency is something that I'm going to need. Well, the only way that I can get frequency from wavelength is using C equals lambda nu. So I got to use both formulas. So that means I'm going to need C, which is 3.0 times 10 to the 8 meters per second. I'm going to need lambda, which is 6.91 times 10 to the -7 meters. And now I can calculate frequency. So starting with this so that I can calculate my frequency, I know that frequency is equal to C over lambda, so 3 times 10 to the 8 meters per second. divided by 6.91 e negative 7 meters. My meters will cancel, leaving me with 1 over a second, or hertz. And I plug this into the calculator, and I get 3.8 divided by 6.91 negative 7. So I get 4.34 E14. There's that 14 again. Whoa, negative 14. No, positive 14. Did I do negative on the last one? Dude, I'm sorry if that was confusing. That should always be a positive 14 because visible light has a good high frequency. And then the units on this should be hertz. I'm really sorry. I think I did put a negative 14 on the slide 2 slides before. But fix that. I'm sorry. It should be positive 14. So now I'm going to take this number and plug it in right here. 4.34 times 10 to the positive 14 hertz. And so now when I go to work out my energy equals Planck's constant times frequency. So that's 6.626 times 10 to the negative 34 joule seconds times 4.34. I'm going to run out of room. Times 10 to the 14 hertz. Woo, I managed to get it in. The seconds and the hertz will cancel each other out because remember, a hertz is just a 1 over a second. And then you multiply these two guys and you get something. Whoa, that's not what I meant to do. And you get 2.88 times 10 to the negative 19, and the only unit that's left is joules, which makes sense because this is energy. And again, just like you'll get 10 to the negative 7 meters on visible light, you'll get 10 to the 14 hertz on visible light, you'll get 10 to the negative 19 joules on visible light. And this is for an individual photon of energy. So 1 photon of magenta light will have an energy amount of 2.88 times 10 to the negative 19 joules. 1 individual photon. This wouldn't even be enough energy for your eyeballs to register it. You wouldn't be able to see this at all. You would need like a mole of these magenta light photons to be able to actually see this. Love that picture. This led, Planck's work and Bohr's work led to Einstein's dual nature of light, that electromagnetic radiation does behave as both a wave and a particle. And so he defined the word photon that I was just using on the last page as a particle of electromagnetic radiation with no mass and carrying what he called a quantum of energy. So God love Einstein. He's such a peacemaker. And that leads us to the hydrogen emission spectrum. And you know what? I think I'm going to call it quits because I think these are getting pretty long. Yeah, they are. And I will do the second half of these notes in a second.